Welcome to qnawire.
Problem 11.17, we have a beam attached to a wall by a hinge, and it's supported by a cable. The beam is 9 meters long. The maximum tension that the cable can support before it breaks is 1 kilonewton. And so what we'd like to do is draw a free body diagram of the forces acting on the beam. We want to find what the maximum weight of the beam can be before the cable will break. And then we want to find the x and y components of the force that the hinge is exerting on the beam. And then we want to know whether the vertical component of that is positive or negative. So, or another way of putting it is it directed upwards or downwards, because whether it's positive or negative will depend on whether we put our y-axis going up or down. So to begin with, draw our free body diagram. So we have our beam. Halfway along it, the weight will be acting. A bit to the left of that will be the tension in the cable, which has its x and y components. And then the force from the hinge will have a component we'll call h sub x, and then we'll have the y-axis going downwards. Or we'll say that the h sub y is downwards, and if we're wrong about this, then we just get a negative number, and then we know it's actually pointing the other way. And as usual, we're going to call the counterclockwise the direction of positive rotation. And another thing we should do before we go too much further is figure out actually, what is the distance between the hinge and where the cable attaches, which we can call L. And so this is fairly straightforward, because we know that L squared plus 16 meters squared is equal to 25 meters squared. 25 minus 16 is 9, and so L is 3 meters. And then furthermore, the angle theta that this makes is going to be the arc sine of 4 meters divided by 5 meters, opposite over hypotenuse. And so theta's value is 53.1 degrees. Good. So the maximum weight we can find using our equilibrium condition for the torque. Tau goes in the sum. And this gives us that the tension, the magnitude of the tension, which we'll set equal to the maximum 1 kilonewton, because we want to know the maximum weight, times the sine of the angle, because only the vertical component of the tension exerts a torque, because it's a cross product. And if a force, or a vector in general, is directed in the same direction as another vector you're taking the cross product of, the value of the cross product is 0. This will be times our L, which is 3 meters, minus the weight of the beam, times our 4.5 meters, if we call the entire length of this big L, L over 2 is equals 0. And we don't have any forces from the hinge because we're setting this equal, or not equal, but we're using this as the axis about which we're computing the torques. And so then solving this for the weight, we have TL sine theta over L over 2 is equal to the weight. And again, using our 1 kilonewton maximum tension gives us the maximum weight, which is going to be 533 newtons. Now in part C, we want to find the components of the force that the hinge is exerting. Start a new page for this. So here we'll use our other equilibrium conditions, that the sum of all of the x and y components of the forces acting on the beam have to be 0 because it's not accelerating, or we don't want it to be accelerating. So for x, this gives us the vertical component of the force from the hinge minus the horizontal component of the tension in the wire has to be equal to 0. And so then you just add this to both sides. And so this is going to be our 1 kilonewton times the cosine of 53.1 degrees. And so the hinge is exerting a force of 600 newtons to the right. For y, recall that we have h sub y in the negative y direction, which may or may not be true. And if it's not true, we'll get a negative number, and then I'll know it's actually upwards. So we have the horizontal, or the vertical, rather, component of the tension minus the y component of the hinge force minus the weight. All add up to 0. Then adding this to both sides, and h sub y equals just the difference between the vertical part of the tension and the weight. And this has a value of 267 newtons. Which means that the force is in fact downwards.